For many thousands of years, physicists assumed that atoms were the smallest building blocks of matter. But atoms are made up of even smaller particles, subatomic particles. In 1897, the British physicist Joseph John Thomson discovered the first of these particles, the electron, which orbits the nucleus. For this he received the Nobel Prize in 1906. 5 years later, Rutherford discovered the nucleus, and 7 years after that, the proton, one of the particles that make up the core. The second subatomic particle, the neutron, was discovered in 1932 by James Chadwick. Both physicists also received the Nobel Prize. In experiments with electrons produced by radioactive decay, it seemed as if energy was being lost. In the 30s, the Austrian physicist Wolfgang Pauli postulated the existence of another subatomic particle, which is responsible for the loss of energy. He called these particles neutrinos. His theory was not proved until the 50s. Neutrinos are primarily produced by nuclear fusion in our Sun, as the German physicist and Nobel laureate Rudolf Mörsbauer explained in 1982 in Lindau. Thus, the fusion of protons, which includes the conversion of protons into neutrons, only works if there are neutrinos present. This means that our existence is ultimately dependent on the existence of neutrinos. So far, 3 types of neutrinos are known to exist: the electron neutrino, the muon neutrino, and the tau neutrino. They have such a weak interaction with matter and so little mass that they can travel at the speed of light through anything. Every second, 60 billion neutrinos per square centimeter reach Earth from the Sun. However, this solar power cannot be fully measured. Mörsbauer has an explanation. It could be that the neutrinos coming from the Sun to us experience oscillations so they convert into other types of neutrinos. That the Sun's electron neutrinos are transformed into muon neutrinos and tau neutrinos and are then all mixed together. Therefore, only a third of the neutrino flow from the Sun can be detected. Another very fundamental question was still unanswered at the beginning of the last century. What holds the nucleus together? Theoretical physicist Yukawa suggested in the 30s that it was the strong nuclear force and meson particles. The American Muray Gell-Man explained exactly what a meson was using the quark model in 1964, for which he received the 1969 Nobel Prize. According to this model, there are 3 fundamental quark particles: the up, down, and strange quark and their respective antiparticles. A meson is made up of a quark and an antiquark. It holds together the protons and neutrons in their nuclei. These in turn are also made of quark particles. With the discovery of cosmic radiation by the Austrian Victor Franz Hess in the 20s, yet another elementary particle was found, the muon. A little later, physicists found more than 100 new subatomic particles during the first experiments with particle accelerators. They all follow the same periodic patterns. Physicists used these to develop the Standard Model. And so the building blocks of matter, their masses, and the forces that hold them together set up a kind of physical periodic table of elements. But where do the particles get their mass? The symmetries of this model do not allow this. This led to a new theory, which the American Nobel laureate in physics David Gross explained in 2008 in Lindau.
But an important aspect of the Standard Model is the mechanism for the breaking of the symmetry, the local symmetry that underlies the weak interactions. There is an ansatz, there is a theory for how that symmetry is broken, called the Higgs mechanism, which predicts, in the simplest version, a particle, a very distinctive particle, which hasn't yet been observed.
The Higgs mechanism is named after British physicist Peter Higgs. According to his theory, there is a field that gives matter its mass. Finding the associated particle, the Higgs boson, is essential, as the Dutch physicist and Nobel laureate Martinus Veldman said in 2010 in Lindau.
The standard model
The standard model is a complicated model in which the Higgs plays a role, and it has to be there, that much you can deduce for sure. But on the other hand, the common standard model is complicated, as there is lots of particles with masses of which you have no idea why they are at that particular value, with forces in some balance, but why we do not know. With the Large Hadron Collider at the European Nuclear Research Centre, CERN, near Geneva, scientists are searching for the so-called God particle. The most powerful particle accelerator in the world is an almost 27-kilometer ring of superconducting magnets. Two proton beams traveling at close to the speed of light collide with an energy output of up to 14 trillion electron volts. Long before the construction of the LHC, Nobel laureate in physics Werner Heisenberg welcomed such a European project in 1971 in Lindau.
Ein großes wissenschaftliches Projekt.
A large scientific project whose importance is recognized by all, but because of the high cost, which cannot be borne by a single European country, it represents an ideal case for true community work. Heisenberg was right. At CERN, scientists from all over the world now have the first indications of the existence of the Higgs boson. Soon, they hope to be able to answer the question of the origin of the mass of elementary particles. Only then will the standard model of physics be complete and the interaction of the basic building blocks of matter be clarified.